Alright, so I'm going to just start over the problem that we started solving in class on Friday, March 21st. So, let's pretend we didn't start it already. And if you take a look at the problem, like I said, is first we see that we have case 1, and then at time t later it is case 2. So the two things that are different are the magnitude of the magnetic field and the angle at which it's oriented in that magnetic field. So we have a few questions to answer. We have to answer in terms of the terms given: LR, B naught, B1, T, and rho and A. So as always, I'm sorry, not A, that's part of the problem, but as always that means that if we have other terms we have to rearrange them to make sure we only have one term. Okay, so let's take a look at the first one. It says in terms of R and L, how many loops are in the coil of wire? Well, L is the length of the wire, and then the R is the radius as defined right here. So what we can do is kind of talk about a relationship between the coil of wire and the length. So notice that this is basically just a stack of single loops, right? So one loop, the circumference is, we say this is number 1, the circumference of that loop is 2 pi r. But if we have a stack of those loops, then we basically have whatever the circumference is times the number of loops. So the number of loops is going to be, or the length, or we can say this, is that the total length is the stack of loops. So total length equals stack of loops. So that's why I'm going to use the L here. This is the length of one loop, and this is N for stack of loops, the number of loops. Therefore, the question is, in terms of R and L, how many loops are there? So N, if I divide that out, it's going to be L over 2 pi r, like that. So that's number 1. Pretty logical. Total length divided by one circle will give us the number of loops. Okay, the second part says, what is the induced voltage over a period of time t? So induced voltage is going to be a number of loops times the change in flux over the change in time, like this. So what we're going to do now is set up our relationship. Now there's two things that are changing, both the angle and the magnetic field. So although I did it slightly different in class, it's still the same way. So I'm going to actually do it a little different, and it's good to see different perspectives anyway. So more or less something's got to change within the confinements of magnetic flux, defined as this. So change in magnetic flux over change in time. So the thing that is going to remain constant is A. So actually I'm going to bring that out here. So I'm going to write this all equals to N times area. And the thing that changes is the magnetic field over time. So again, these things are not changing. This is the stuff that does change. So coming over here, I'm just going to keep going with this. So N times A is going to be equal to the change in the magnetic field. So the magnetic field here is going to be B times cosine of the angle. In this case, the angle is 0. So the cosine, I'm going to get rid of that. The angle here is 0 degrees, so the cosine of this would be 1. So basically this is just going to be B naught. But this is not. This is going to be cosine, B1 cosine of whatever that angle is. So I'll just actually leave it as that. So the change in magnetic field and the change in the angle would be written as follows. So final minus initial. So this is the final. This is the initial. So final is b1 cosine angle 1 minus the initial, which is b naught. Now you could write cosine as 0, but remember cosine of 0 is just simply 1. Now this is happening all over a change in time, but notice how time here is 0. So same thing, delta t is technically going to be t minus 0. Final minus initial, so I'm just going to write it as t. This is absolutely correct as well. So this is a little nicer. In class I was going to get to this point, but you could see it here too as well. So now I can't use n and I can't use a because those are our parameters that allow us to write this problem out. So actually I have to now put in a and put in, n and a in terms of what we have. So we already have n as L over 2 pi r. Now a is the area which it cuts through, so the area is going to be that of a circle. So a is the area of a circle, which is pi r squared. So pi r squared times all of this stuff. Oops, not I. Cosine 1 minus b naught all over t, like that. So now you can see pi's cancel, one of the r's cancel. So then our relationship now becomes LR over 2t b cosine. I guess I don't necessarily need to put the 1 there because it is just listed as cosine like that. So you know what, I'm going to get rid of that 1 right there. Like that. And ta-da! That's, there we go. We have everything in terms of the given parameters, and that is our, well, that was our induced voltage. That is what we were solving. So that is the official answer there. So C says current. So current is going to be V over R, but R, there's no resistor here. This is going to come from the resistance of wire, because it's a really long wire, so the resistance does matter at that point. So I'm going to take our V from here divided by the relationship of resistance in terms of the length of the wire divided by the area. So remember that resistance is, I gave it to you in class as well, was rho L over A. And once again, we can't keep it as A, we got to write it in terms of this stuff. So combining this one and this, we get this. I is going to be, here we go, LR B1 cosine 1 minus B naught over 2t. Now we're going to divide by r. So what I'm going to do is take the reciprocal of that, because that's the same as dividing by 1 over r. So that gives me pi r squared on top. And then it gives us, let's see, rho, which is something we can use, because remember in the problem they gave you that. Like this. Oh, I apologize. Take a step back. Sorry, I just read the problem. We actually have to use A here. This is the area of the wire, so I apologize, not of the circle. So let me get rid of that. Sorry. We can use little a. I'm glad I caught that. So it's actually little a. And that's fine. So I knew it looked a little weird. Okay, so now rho L on the bottom, little a on top. Okay, which basically just gets rid of L, and everything is back to something that looks more or less like this. R little a, Ra, like that. all over 2t rho. That's our current. Oops. Darn. It's hard to draw a straight line. There we go. Alright. Now part D asks, why is it independent of L? Two things. One, first of all, you can see that L's cancel. So that is what they refer to as the, the independent of L part. But basically, in short, what happens is that R is related to both voltage and resistance. So yes, the length of wire, if we increase the L, the length of wire, we're going to get more voltage just through this relationship, and you can see that there is a factor of L. However, counteracting that is if we increase L, well, we actually increase resistance. So what you get is current is not affected by L, because if we have V over R, we increase the voltage, we increase the resistance. Basically, these kind of cancel each other out. It keeps the ratio the same. So that is the conceptual reason of why this works. Alright, if you have any more questions, let me know. If not, that'll be it. Also, just a quick note about this as well. Notice that for the most part, we never really consider length and current anyway. It's dependent on the voltage and the resistance. There's no L dependence. Even if I talk about in terms of charges and time, there's no L dependence. So there you have it. Alright, have a good weekend, and I'll see you on Monday.